Okay, welcome everyone. This is New England Dynamics and Number Theory Seminar, and our speaker joins from India. This is Gaurav Aggarwal, and the title of his talk is Joint Equidistribution of Approximates. Welcome, Gaurav.
First of all, I would like to thank the organizers for giving me this opportunity. Today, I will be discussing about the joint equidistribution of approximates, which is based on a joint work with Anish Ghosh. Now, one of a problem that is well studied in history of mathematics is finding a necessary and sufficient condition for expressing a natural number as sum of three squares. And as is well known by legendary theorem that as long as the integer n is not of a particular form, such expression is always possible. Geometrically, this is same as asking that for what integers n, the sphere of radius root n contains an integer point. So now the natural question that comes up is that how does these integer points equidistribute on the sphere? And in order to study these, we project these points onto the unit sphere and see how do these equidistributes. In 1950, Linnik proved that as long as the sequence of integers tending to infinity satisfy a certain congruence condition, the projected points equidistribute on the sphere with respect to the usual Haar measure on the sphere. Duke in 1988 proved this in full generality without assuming any congruence condition on the increasing integers by relating it to the study of Maaß forms and based on the work by Ivanek. In 2011, Einsiedler, Lindenstrauss, Michel, and Venkatesh generalized this to higher dimension. And in 2015, Aka, Einsiedler, and Shapira generalized this problem to the study of joint equidistribution. Now, you take a sphere of radius root n, you look at the integer point, they associated two objects with it. One is its projection onto the unit sphere as over here. And the second is the shape of the lattice obtained by intersecting the set, looking at the integer points on the plane perpendicular to V. And they call it, which is also called as Heegner point associated to the vector V. Now, the problem became much more difficult because even though individual objects do equidistribute in their respective spaces, it's not guaranteed that the tuple or the pair equidistribute in the product space. And due to this difficulty, they could only prove that as long as the sequence of integers tending to infinity satisfies certain congruence condition, these pair actually equidistribute in the product space. And conjectured that the condition, this congruence condition is actually superfluous and can be removed. In 2015 only, Anish Ghosh and Zeng considered a very similar flavored problem. Now, earlier we were having a manifold and we were looking at the integer points on it. Now they change the problem a bit and said that, okay, instead of looking at the integer points, you look at the points of a random lattice. And instead of the moving manifold, you look at the increasing domains. So they considered chose a random lattice. They studied how does the points of this random lattice are equidistributed in the above form of increasing domains by projecting them onto the unit sphere and seeing how does they equidistribute. The reason for considering this kind of a surface was its relation with Diophantine approximation, its application in Diophantine approximation. And later on, Kleinbach, Weiss, and Alam Ghosh generalized it in different directions. In 2022, Shapira and Weiss generalized this problem to the joint equidistribution. Now, you have chosen a fixed lattice, you have a point in the above domain. They associated two objects with it. One is as its projection onto the unit sphere, and the second one is the projection of the lattice on the plane RD cross 0 along the vector V. the random lattice chosen. And they proved that for almost surely with probability when 1, these points actually equidistribute in the product space. The main idea in the proof of Shapira and Weiss was the construction of a cross section for a diagonal flow on the space of all lattices in dimension D. So let me introduce what these terms mean. Now, flow just means an action of real line on the space. For example, the geodesic flow on the hyperbolic surfaces. Uh, how I think of the flow is that we have a certain space that's actually evolving over time, and the trajectory of particle as time increases actually captures the action of real line on the space. The second word over here was the cross section. Now, cross section for a flow, for example, here in the diagram would mean that you it's a subset of the full space so that you take any point in the space and flow it around. It will come to this cross section infinitely often, both in positive and negative time, and it will not stay on the cross section. It's not, in some sense, it's perpendicular to the flow. Mathematically, it will exactly mean that the times so that the point actually ATX belongs to the cross section is both discrete and totally unbounded. With any cross section, we associate two natural functions with it. That also will explain that what's the reason for why a cross section is actually interesting to people. Like, why do we study the cross section? Now, suppose we have this space and we have a flow on it. Suppose this thing is a cross section of the space. You take a point on it. One can flow it around. Now, since this set is a cross section, as we keep flowing around, it will return to the cross section. Suppose B is the first point to which this flow actually return back in the cross section. Then the point B, the function which sends A to B, the point to which so f of a is the point to which, if you take the flow from A, the point where you will hit the cross section for the first time is the point B. And the return time map is actually the time you would take to move from this point A and reach the point B. Mathematically, it's given by the minimum of the time t, so that ATX belongs to S again, and the return time map as just A tau x. Now, the reason for studying this cross section is that this cross section with this return time function and first return time map actually captures all the dynamics of the larger space. Meaning, if you just know these three, this cross section and these two functions associated with it, one can reconstruct the whole space from this information. In particular, it's just the suspension of the dynamical system SAS, the cross section with first return time map with the root function, the return time function. And usually in the most good scenarios, if one choose the cross section very accurately, then this cross section actually behaves as a very simpler dynamical system in a larger dynamical system, which has all the information of larger dynamical system, but is much easier to study. So we usually people can get a lot of information about it from it. Now, a natural question that appear up is that what's the suitable analog of this cross section for multi-parameter flow? Whereby a multi-parameter flow, I mean that action of RD for the space on the space for D greater than equal to 2. Now, if we think that, well, cross section is just a subset, so that doesn't stay over here and like leaves immediately and hits infinitely often, then definition can be made similarly, that it's something like a codimension D. For example, action of art, it's a codimension 2 object in the full space, so that it's coming back infinitely often to this space. But this can, yeah, this definition do make sense. But the main problem is that there is no analog of like first return time map. There is no suitable dynamics on the cross section, which actually like is enough to carry forward all the information of larger dynamical system and like fit on the smaller cross section. Okay, we don't have the dynamics, but still, if we construct the cross section suitably, can we actually extract a bit some information from this smaller like cross section? If we construct a cross section, what would be that information? So in joint work with Anish Ghosh, we actually studied that what properties of the cross section for this multi-parameter flow can be used and like sorry, what properties of the multi-parameter flow can be derived by studying the cross section, and we used it to study the multiplicative Diophantine approximation and proving certain results. Now, before proceeding, let me just introduce what does this term Diophantine approximation means. So in Diophantine approximation and multiplicative Diophantine approximation means. Now in Diophantine approximation, the main goal is usually to approximate a real number by a rational p by q in the most naive form. And so that both the denominator q and the error term is small. So it's natural to look at their product, q times alpha minus p by q, which is alpha dot q minus p. Now, I have a certain reason why I wrote in this form, alpha dot q minus p. The reason is that because while generalizing to high dimension, this kind of form actually helps. So instead of thinking alpha is a real number, think of alpha as a real map, linear map from real line to real line. What does this term exactly means is that you have a linear map, you are feeding it integers and trying to approximate it by integers, alpha dot q minus p. So in high dimension, it suitably means that you take a linear map from dimension Rm to Rn, you feed to it an integer q vector and try to approximate it by integer p vector and ask that, okay, can I make sure that a dot q plus p and q, both of these terms are small? Now, multiplicative Diophantine approximation is the rule which tells us that which vectors p and q should be considered as a good approximations and which should not be considered as a good approximation or bad approximations. So for this, first of all, we decompose this m as sum of some certain integers. Yeah, so that we fix the integers n1 to mk, fix n1 to nr so that their sum up is n and m respectively. Corresponding to the decomposition of m as m1 plus mk, you decompose the a into row vectors a1 to ak's. Now, a PQ will be called as a good approximation if this term is actually less than epsilon. So, where just to inform, this Q1 to QR are like the decomposition of the vector Q according to this n is equal to n1 plus nr, and P1 to Pk is the decomposition corresponding to m1 to mk. Now, for the rest of the talk, I will refer to all the solutions PQ as satisfying this inequality as the epsilon approximates of the matrix A. In the simplest, most possible case, this is same as asking that you have two real number alpha and beta. You're trying to simultaneously approximate them by the real, simultaneously approximate them by rationals, such that denominators are same. So alpha dot q plus p and beta times q plus p prime. And this is like the form that's been in the Littlewood conjecture, which is the one of the most famous problems in the Diophantine approximation, which says that you take any two real numbers, alpha and beta, there is a solution, a sequence of integers, pn prime qn, so that the error term actually converges to zero as n tends to infinity. And the best result known so far is that the set of exception to this conjecture has Hausdorff dimension at most zero, and by proved by Einsiedler, Katok, and Lindenstrauss. Now, our main result okay, says the following. So fix the linear map A and decompose it according to the approximation M, according to the decomposition of M as M1 to Mk as into rows A1 to Ak. You look at the epsilon approximates PQ so that their GCD is 1 because we don't want overcounting in some sense. And with each approximant, you associate the following terms. First is the projection of each individual term onto the sphere. So P1 plus A1Q, which is the error term projected onto sphere. The second term P1, P2 plus A2Q, so on. And also project the approximation vector Q onto the unit spheres. The second is the error term with between 0 and epsilon, because this is an epsilon approximant. Third is a lambda APQ. So I will not define this term for this presentation because I think it will get a bit complicated. The term is a bit involved. But this lattice should be thought of as containing the information about the relative size of the terms P1 plus A1Q, PR2AQ, norm of these elements, individual elements. And the fourth one is the solution itself. So our result is a result about the joint equidistribution, which says that with the probability 1, for our choice of weight, the associated objects to the approximants actually equidistribute in the product space. Meaning, there exists a conal subset of M cross N R, so that I take any in that conal set and look at their epsilon approximants and look how does these objects equidistribute in the product space, then we will see that they actually equidistribute in the product space. Now, just some comments. First of all,
excuse me, can you explain? Maybe I missed it. What is this Z hat? It's not integers, something else?
So Z hat is actually the profinite completion of Z.
Profinite completion, okay.
Profinite completion.
So you just embed it into profinite completion? Because you start with P and Q, which are integers.
Sorry. So Z being embedded, Z to the power M plus N being embedded in Z hat as like the Z cap being profinite completion.
Okay.
And the reason for considering this Z hat is that it actually allows us to put congruence condition. So for example, we want that PQ to be actually equal to something mod N. That condition is actually being captured by this Z cap to the power M plus N. And in order to study it, we actually had to study the multiparameter diagonal flow on the adelic space. So, is it clear? Or? So, yeah. So, this result not only gives another proof of the result by Shapira and Weiss, but also generalizes the result. The result is actually the same result, but with condition that this matrix should be actually a vector. And you're not actually looking at the multiplicative case, you are actually looking at additive case. So this vector Q1 to QR should be 1 and this k should be 1. Sorry, I messed up here. It should be a. Sorry. But they say that this and a result removes this condition. A result is not only about this joint equidistribution, but also proves the asymptotic of number of epsilon approximate with the constraint. So congruence condition, the projection onto the sphere, like you want the certain projections to hold the lattice, so that it kind of captures the ratio of the individual things, and the error term being less between the thing. And the second main result is about the best approximates of the uh, almost every lattice, sorry, matrix. So let me start. What do I mean by a best approximation? Now, suppose PQ is called as the best approximation for a real number alpha if the error term Q alpha plus P obtained at the level Q is actually smaller than all its previous values. So Q alpha plus P, this error term is smaller than the error obtained at earlier levels, Q prime alpha plus P prime, where Q prime being less than Q. And it's well known for the real alpha that these are exactly given by the continued fraction of the alpha. The Levi-Khinchine theorem gives that if you look at the best approximates P and Qn of the real alpha, and you try to see how does Qn behave, then it actually behaves exponentially. So 1 by n log Qn actually converges to a finite value. Doblin, Bosma, Jagan, and Weidach prove that you look at the error term between 0 and in the interval 0, 1 and see how does it actually equidistribute, how does it distribute on the real line. Then it says that it actually converges to a measure nu, which is actually independent of the real number alpha for almost every alpha. In high dimension, the natural definition should be that the only solution PQ will be called as a best approximation of a real matrix A if the only solution P prime Q prime satisfying the condition that the error at the level Q is actually larger than the given value, and Q prime being less than Q is okay. Sorry, it exactly. So PQ will be called as best approximation for a matrix A if the error term obtained at level Q should be smaller than all the earlier values, which is equivalent to saying that at all the earlier values, if we get some Q prime such that error is less and it's also at lower level, this thing is not possible. So the only solution should be PQ and minus PQ. And Schung-Schwalier actually proved that if you take these norms on Rm and Rn as the Euclidean norm, then the denominator Qk, so it's not actually denominator, it's actually a vector, but roughly it plays the role of denominator. So I will call it as denominator. So even in high dimension, this denominator actually follows like a log exponential growth. And the error term also decreases exponentially. And they actually satisfy a certain relation between them. Shapira Weiss generalized this to all the norms, but providing the condition that n should be equal to 1. And they proved that the denominator actually behaves exponentially, the error term converges exponentially. And the third one, as earlier in the dimension 1 by Doblin, Bog, others, et al. It says that the error term actually we distribute on the space Rm according to this for some measure mu. And in our paper, as a corollary of our main result, we will get that this condition that n is equal to 1, or the condition that the norm should be actually equal to Euclidean norms, is not required, like it can be removed. Now, let me define how we define the best approximation in the multiplicative case. As again, we take a decomposition of integer m as the sum and of m1 to mk, and n as the sum of n1 to nr. Corresponding to this decomposition, we again decompose A as into rows. And the definition is says that, which we defined is that we will call the vector PQ in Zm cross Zn to be best approximant of A if the only non-zero integer solution satisfying the inequality that corresponding to this decomposition, the error should be less in all the cases, and the norm of QJs is less than all cases. This thing is not possible. In other words, so it's a multi-level thing. So the levels is now given by this decomposition. So we have the vector Q. Earlier, the level was the norm of the Q. Now the levels, it's a multi-level thing. So Q is decomposed into Q1 to QR. So the level is norm of Q1, norm of Q2, norm of QR. And you're saying that now look at the integer points which are below these multi-level. So Qj prime, so that it's actually less than each multi-level, the Q prime. And the error term is also less than at each of these multi-levels. This thing is not possible. So then PQ will be called as a best approximant of A. Now our main result actually is a counting and like equidistribution results, which says that there exists a conal subset of M cross NR, so that you look at the best approximants of this matrix A, which satisfy the following conditions. So you look at the individual terms, the P1 plus A1Q, P2 plus A2Q, so on up to PK plus AKQ, and the vectors Q1, QR, project them on respectively onto the sphere, and they belong to a particular set. Secondly, the error term is between, say, alpha and beta. The lattice lambda APQ, which is in the space of all lattices containing 0, 0, 0, 0, 0, 0, comma 1. That's in a particular set. And the fourth, something like the condition that PQ is actually equal to L mod n, which can also be termed in the form that PQ actually belongs to a certain subset X4 of the Z hat of M plus N. Then the number of best solutions are asymptotically given by the following rate, the Tk plus Rn R minus 1, and new time the measure x1 cross x2 cross x3 cross x4. And the measure nu is actually independent of A. So it doesn't depend on the choice of A, and is actually absolutely continuous with respect to the product measure. And we actually gave a explicit description of it by it's actually some push forward of the cross-sectional measure by using the idea of the cross-section. Now let me explain the main idea used in the proof of the main ideas of the proof. The first step is actually that we have a problem in number theory. We use the Dani correspondence and translate this problem into dynamical system. So, for example, I will be giving a proof of the case with, which is the same formula as considered in the Littlewood conjecture, Q times Q alpha plus P, Q beta plus P prime. In that case, we can easily see that the approximates, any approximate P, P prime, and Q, they exactly correspond to the points of the lattice lambda A, which is 1 identity alpha beta 0 1, that thing in the region given by z mod x mod y being less than 1 epsilon. So this region with bounded by mod x is equal to 1, mod y is equal to 1, less than equal to 1. Once we have translated the problem into dynamics, that it's actually correspond to picking a random lattice and looking at the points in the, again, the increasing domains. The second step is like the construction of this cross section for the multi-parameter diagonal flow. And in our case, the simplest possible case, the cross section is exactly given by the space of all lattices, which contains a point in one of these four lines, which are lines joining plus minus 1, 0 to plus minus 1, epsilon, the error term epsilon. And we say that, and we observe that. So as we earlier said, any Diophantine approximate PQ exactly correspond to a solution in this kind of a domain. By constructing a cross section, we will observe that any point in this space exactly correspond to a time t, so that the lattice, when we float under this multi-parameter flow, will hit this cross section. The third step is proving that under this multi-parameter flow, almost every lattice is actually generic. So,
Can I
the
ask
first
something?
step, yes.
Just about this construction of cross section. So for one parameter flow, you had the definition that the set of visits is unbounded in both directions. Is it
Yes.
the same definition? I mean, you need unboundedness in all directions of this acting space. Is the set of visits, do you want it to be? I mean, what is the requirement for the set of visits to count as a cross section? Is it supposed to be a lattice in RD, for example, or something like this?
Okay. So since
Do you
we are
have any
looking
assumptions?
okay. If I heard the question correctly, so in our case, we are actually looking. So the definition we gave for the cross section for the multi-parameter flow was that the time should be discrete. We have not included the definition being the unboundedness. The reason for this is that the space we are actually looking at is actually the space of all lattices, and the multi-parameter flow is actually ergodic. So this totally unboundedness for almost every point is actually being granted, like it's for sure. So we have not included it in our definition, but for generic spaces, I think we should have.
Okay, but so you have ergodicity, you have unbounded, but not unbounded in every direction.
No, no.
Okay, I understand. All right, thank you.
Yeah. And the third main step is actually genericity for almost every lambda under the multi-parameter flow. So what do I mean by genericity? And like almost surely every lambda under the multi. So what we discussed in the paper was that suppose we have this, okay, let's discuss the dimension one case. So it's been a theory developed by Kakutani and Ambrose, which said that you're given a cross section to a one parameter flow, then you can actually construct a measured mu on the cross section, which is actually invariant under this first return time map. And secondly, the main importance was that the measured the measure on the full space actually looks something locally like the product of the measure on the cross section and the real line. So I think it should write a bit. So let me stop sharing the screen for a while and just connect my iPad to it. Yeah, is it visible?
Yeah, yes, seems
Okay.
to work.
So in dimension one, so it's theory by Kakutani and Ambrose, which said that suppose you have this space, you have a cross section, and one have a flow AT, and we have a measure preserving measure mu on the space X, and invariant under AT. Then we can construct the measure mu S on the space S, comma, the first return time map AS, so that mu S is actually invariant under this AS, and the mu locally look like mu S times this real line thing. In other words, if we zoom out this very small space, then the measure on the mu measure on the full space exactly looks like this thing times the real line action, this product measure. In our paper, we developed the theory that similar and yeah, not only this, like there some other constructions like, and this correspondence is actually very good. So if mu is ergodic, if and only if this mu s is actually ergodic under AS. And if we even decompose this mu s into the mu ergodic decomposition, mu, then this will correspond to the ergodic decomposition mu s as mu s. So each mu s corresponding to the measure mu. Now in multi-parameter flow, we developed the same theory and said that suppose you have this measured mu on the space X, but this multi-parameter flow, say AT1, T2, then one can construct a measure mu s on the cross section, but it doesn't have any measures, so dynamic so far. So what do I mean by genericity? There is no dynamics. Suppose I take a point on the cross section and look at the times, look at the set times T1, T2, so that AT1, T2, X belongs to the cross section. Looking at the graph, it would be some bunch of points in the space. Now, by genericity, we mean that if I look at all the points in R2, this plane R2, or this set, say, Ts of x, Ts of x, with norm less than capital T, and look at their, so in other words, I start with the point T and flow it in both positive and negative direction in both the in the multi-parameter flow, but the flow should have the time limit less than equal to capital T. And I will read some bunch of points in different directions and see how does, as I keep on growing this capital T, how does these points actually equidistribute on the cross-section space. So we prove that this actually converges to the measure mu s, the cross-sectional measure mu is constructed over here, which is actually locally should look like the sectional measure in Rn. So I think I will stop and will continue with my slides. Just 1 second. Something is going on. Not able to see my slides.
Yeah, they're not here yet.
Just 1 second. I'm not able to share my slides. Somehow there's causing some issue. Just 1 second for me.
Okay. Let's give it some time.
Yeah, is it visible?
Now it works just as before. Thank you.
Sorry for. So what we proved that is the fact that for almost every choice of A, this lambda is A is actually generic under the multi-parameter flow for the cross section. And the first step was actually to prove that for almost every lambda A, this is actually generic for the multi-parameter flow in the whole space actually. And in order to do that, we had to generalize the argument of Klein-Weiss to the multi-parameter flow, where they developed the theory for the one-dimensional flow. And using these techniques, what we get is that we actually get the lower bound for the number of epsilon approximates and best approximates with the constraints, the asymptotic behavior, the lower bound for this asymptotic behavior. And the final step was to use the Schmidt result without the constraints. And it gave us actually the upper bound for the number of approximates with the constraints. And by squeezing these two things, we actually get the exact asymptotics for the number of approximates with the given condition. Yeah. I think with this, I end my presentation.
All right. Thank you for the presentation. Let's give a virtual round of applause. Are there any questions? So can you say a few words when you mention our paper with Rangang, Shi, and Barak Weiss? What exactly? So which argument you are talking about? And
So
exactly, because that's your generalization look.
in that paper, one of the key result in proving the projection argument for the with the multiplicative case was that almost every point is actually Birkhoff generic, and then you prove the C alpha generic. So the exact result was the following. So you take any point lattice lambda A, you flow it around with the one single diagonal flow, then it actually equidistributes in the whole space. And the idea was to use the fact that the space of all lattices lambda A is actually the unstable horospherical flow. So once translated using this diagonal flow, it actually kind of expands and converges to the measure mu, and that too with the rate exponentially. And then you kind of use the Schmidt type trick to prove that for almost every A, the lambda A, this flow actually converges to the measure mu. Now, we did was that instead of looking at the single parameter flow, one look at the multi-parameter flow and look at the Fourier sequence given by the triangles, increasing triangles in the positive quadrant. And ask that, okay, if we take a point over in this point and look at how does it equidistribute under the increasing triangles. So we have to use the same same idea and say that this lambda A under this multi-parameter flow and along this Fourier sequence actually converges to the Haar measure on the full space and apply the almost the same trick.
Okay, I think I understand. Thank you. Other questions? Okay, if there are no other questions, let's thank Gaurav again. This was good. I think I can even do one of those hands shown as a picture. So thank you all for coming. Thank you, Gaurav, and good luck, and I'll see you guys in a week from now. Thank you.
Thank you.